Good morning, everyone. My name is Cheng and I come from the University of Kaiserslautern-Landau in Germany. And today I would like to introduce you to the topic, image-based semantic recognition and segmentation of concrete images for the assessment of existing concrete structures. So I will go through quite quickly these six parts of my presentation. The first is introduction, then I will introduce dataset preparation and a model for semantic segmentation of concrete surface defects, and then resource evaluation and beam modeling of detected damages. And finally, I will conclude this study. So first, introduction, I will introduce our motivation of this study. So with the growth of surface time and cracks and spalling of concrete structures tend to increase gradually. So I mean, which can affect the safety and durability of concrete structures. So it's very important to collect this information and record it. And this information was mostly collected and recorded manually. So we want to develop automated methods to detect these damages. And damages information is also very important in BIM model. I mean, we want to evaluate the BIM model further. So this damage information is also very important for our task. So this is our methodology in this study. So first we collect some data sets, we do some preparation and divide these data sets into training and validation test data. And then we train the model and UNet network, and then we do the evaluation results. And finally we make damage geometric features extraction. And finally, we achieve this visualization of damage in the BIM model. So first, we collect many images from the peer hub ImageNet. This is an open source database. So we have collected about 2,000 images, and we annotate manually. And use this tool named LabelMe. This is an open source tool. We can easily use it to annotate our images for the training data set. This input image is our true mask. So this number of images, we have totally about 2,000 images, and we have divided it into two data sets, about 80% of training and 20% of validation. So then we have developed a model for our task, for our segmentation task. So first we use transfer learning. So this means we have a pre-trained layers, then we do some fine-tuning, and then get our output layer. So the model architecture is typical. The model is, this name is UNet, but we do some modify in this UNet and to make it clear and easier to use. We also do some. We also use this data augmentation technology to create more image examples from the existing images data sets, and through this image transformation, such as flip, rotation, and transpose. Then I will show you the results and the evaluation. This is our input images and this true mask, which is labeled by our annotator, and this is our predict mask. You can see that from this predict mask, it shows quite good results. It can also predict some damages that which was not annotated by their true mask, but this is actually exists in images. So here we show our accuracy of the training data sets. This is 95%, and for the validation accuracy, we have 94%. But more important, I think, is the test data sets. We have total 7 images, these unseen images by the training model. So we have input these text images to get to show the more accurate result evaluation. So you can see that from the visual perspective, you can see our model performs well. It can predict, or I will say it can also detect many cracks and also spalling of these test data sets. So so I will also do some discussion, because I think data sets of in our studies is not very much. I will say quality of the data set can be increased in the future work, and then we can get much better results. And we can also do much better annotation from the data sets to get much better results. So that's the important part of our study. So we have tried to convert these geometric features of damage into our beam model. So we have tried first the contour, the methods of contour. We try to find out the contours of damages, but you know, the detected area of damages are not continuous. So this means we will get many contours, and each contour will contain many contour points, which is not good for the beam, for the reconstruction this damage in the beam model. So we also try the other method. This means convex hull. So you can see convex hull has even the worse results. Then we have developed the new methods. We have split our images into more and smaller images. In our study, we have split our image into 64 smaller images. Then we generate the convex hull for each smaller images, and in the end, we combined all the small images again into the total images. So you can see that the result is much better than before. So if you want to get much better results, you can split this picture into more and smaller images, such as 1028 images. Then we can get much better results. Okay. Finally, we have generated the contours of these results of the convex hull. So that's good. In the end, we have only 2 contours for our beam modeling. These contours, and each contours has also not much contour points. So. So in end, we have converted these geometric features of damages into our beam model through the IFC format. Finally, I will conclude my study. So in our study, we first collect many data sets and do the annotation manually, and then we use transfer learning and UNet model training for the images segmentation of concrete structure damages. Here is the spallings and cracks. And then we have developed a method for extracting damaged geometric features. And finally, we convert these damaged geometric features into the 3D beam model for the visualization. Okay, thank you for your listening.